Okay, so this is Griffiths Electrodynamics, problem 2.3. We're looking at a point P, which is a distance z, I guess perpendicularly to the end of this line charge of length L, which extends out to one side. Let's go ahead and define our directions real quick. We'll just call this X and this Z. Okay, so we're going to find the electric field up at this point P as a result of this line charge, which, by the way, has a linear charge density of lambda. Okay, so we're just going to use the formula for the electric field, right? And use the line charge version of it. Okay, so we're integrating lambda. Okay, down here we have this cursive r. Up here we have this unit vector cursive r, and then infinitesimal length element. So what have we got here? Let's look at some of the pieces. First of all, this lambda is a constant, so it's actually not a function of this r primed variable. R primed, again, is just the displacement vector, or the position vector of wherever this little piece of charge is located. So it's constant, so it can actually come out of the integral. This cursive r squared is the magnitude of the distance from the source point to the field point. So right here, I'll just call this coordinate x prime right here along this line. And so the length we just get from trigonometry, right? This is a right triangle. So let's just write this out. Just from Pythagorean theorem, cursive r squared is equal to this x prime squared plus z squared. So now we have this piece as well. Let's go ahead and look at our cursive r hat vector, so unit vector. And that's just the unit vector in the direction of this vector from the source point to the field point. Basically that is, well, let's just write it out. So we have a minus x prime in the x hat direction, and we would go up z, so plus z in the z hat direction. And then because this is a unit vector, we need to normalize it to 1, so we divide by the length of this vector, which is just the square root of its length squared, right? So just the square root of this above. So let's write it out. These are both squared. I'll try and write that more clearly, like this. So here is our hat vector. Let's gather the pieces together and just write them out here. So we still have our 1 over 4 pi epsilon naught. And the lambda we're going to go ahead and bring out of the integral because it's constant. And then we just have these pieces inside here. So our integral, we're only going to be integrating from 0 out to L because that's the only place where the charge is. And now we just take this and divide it by this. So we get a minus x prime x hat plus z hat, and this is divided by this thing inside here to the 3/2 power, because we have a half power here and then 2 powers up here. Okay, so 3/2 power, and this dl prime is just a dx prime. We're just calling it, it's all along the x direction here, right? So, all right, so this breaks up into 2 different integrals, and you can see the answers to these integrals in example 2.2. If you don't have your book with you, that, let me see what problem this is. This is, yeah, so if you look at the video for problem 2.4, you can read example 2.2 right at the beginning. You can just pause it at the beginning and read it. But anyway, we'll go through the integration anyway, so. Okay, so we have 2 different integrals. One is a minus, let's put this in brackets and actually write this out. So we have an x prime over this x prime squared plus z squared to the 3/2 power, and integrated with respect to x prime. And this is the x hat, the x direction component. All right, and then we also have the z hat component. Feel free to skip ahead in the video if you don't care about this integration. Long story short, we get one that's a u substitution and one that's a trig substitution. Okay, and this one's in the z hat direction. And there we go. All right, so what we've got now, let's just, yeah, never mind. Let's just focus on each of these integrals separately. So let's go after this integral for first. This is the u substitution one. Okay, so let's go after this one. So I'm going to make the substitution of u is equal to x prime squared plus z squared. Okay, now we just find our u equals 2x prime dx, or yes, dx prime, okay. Now, let me see, so we get a, this 2 is going to come down as a 1/2 out front. We'll deal with the limits of integration in a moment. We're just going to have a du over u to the 3/2 power. Okay, so 1/2. So we have a u to the minus 3/2. So that's going to give us a u to the minus 1/2. And then we divide by minus 1/2. Downstairs, kind of awkward, right? But we get a minus u to the minus 1/2. And since we're this far, let's just go ahead and plug the x back in, and then we'll do our limits of integration straight from 0 to L. So we get a, again, we have this 1/2. No, we don't, because this other 1/2 cancels it. Sorry about that. So we have a minus 1 over u to the 1/2 power. So x prime squared plus z squared, and this is under a square root. And we're back into the x land, so we're just going to go from 0 to L. Yes. So, where are we? Let's just take this minus sign and reverse the limits of integration. We get a 1 over z minus a 1 over L squared plus z squared under a square root. All right, there we go. So here's, we'll end up plugging this in for our first integral here. We'll try and remember where it is. All right, so now onto our trig substitution one. I'll go ahead and write this as an indefinite integral, solve it, and then go back to definite integral once it's done. We can bring the z out front. This z, it's not being integrated over, just a constant. And then we have a 1 over x prime squared plus z squared. Okay. All right. So here we go. Let's write out our substitution real quick. So we are going to use a tangent. All right. So let's make the substitution. X prime is equal to z tangent of theta. All right, and let's draw our little triangle out. So if this is theta, then we have an x prime here, we have a z here, and here we have x prime squared plus z squared all under a square root. All right, so here's our substitution, our little triangle. We're also going to need the differential, so dx prime. Let's see, the tangent, it just gives us a secant squared. Square root of theta d theta. Okay. All right, let's write this out a little bit more up here. 1 over, so we will get a z squared tangent squared downstairs, and then with the 3/2 power that becomes a z cubed. So we have a z cubed downstairs, and then we have just a 1 plus tangent squared of theta, and that's to the 3/2 power. And then plugging in our dx prime upstairs, we have a z secant squared of theta d theta. Okay, we're getting kind of cluttered here. We can squeeze a little bit more down here maybe. Draw a little arrow. All right, so now we get a 1 over z. 1 plus tangent squared is just equal to secant squared. So we get a secant cubed on the bottom. Let's just write this out real quick. So we have a secant cubed theta, and then up top we have a secant squared. Okay, so we just have 1 power of secant on the bottom. So that divides out to 1 on top. And 1 over secant is just cosine. And let's just do it in one step. Anyway, integral of cosine is just sine. So we have a 1 over z sine of theta. Okay, And then, of course, plus some constant, whatever, since we're doing an indefinite integral. So now we come back and we substitute in our, our last line. I'm going to not worry about the, well, we'll put it in front. There's our constant. All right, now we want to substitute back in our get back our x's and z's and stuff from this sign. So we take back a look again back at this angle, and the sine of this angle is just this side over the hypotenuse. So we have a 1 over z, and then we just have an x prime divided by x prime squared plus z squared under a square root. All right, so where are we? We have just solved this integral, I believe. And I think, okay, I think we're good. All right. So let's plug these back in and just see what we get. So back here on our original electric field, we have a 1 over 4 pi epsilon naught. We have a lambda. Now we need to go dig up our previous result, if I can find it, which was this right here. And remind ourselves what we solved for. We did not put the minus sign in here when we solved for it. So we need to go ahead and put the minus sign in there. So we get a minus 1 over z plus 1 over L squared plus Z squared. And this was our part that was in the x hat direction. Okay, so that's our, what a mess, right? What a mess. Here's our first piece. Now we need to plug in our second piece. And we solved for that right here. We are evaluating this from 0 to L. Right. So we wanted to put a limits of 0 to L on this. Kind of skipping around a little bit. All right, and the L just plugs into the X. So when we put in a 0, this just goes to 0. So we can just plug this right in with an L, and we should be good. 1 over Z, we have an L over L squared plus Z squared. And this was our component in the Z hat direction. Okay. Okay. Put brackets on there. All right. Let's go ahead and factor out a 1 over Z because we can, and see if we can clean this up at all. But this is our final answer for the electric field at point P. So once we get this written, we'll look at the limit for Z much greater than L. And we should recover a point charge. Make these parentheses a little bigger. Oops, this is our x direction. And then we just have an L over L squared plus Z squared. And now I start writing an X, of course. Here's a Z hat direction. All right, so here's our final answer. This is our electric field at the point P up a distance Z above the end of a line charge of length L. This situation right here. With, of course, a constant linear charge density of lambda. Here's our answer. So now, maybe up in this corner, we can talk about what happens when we want to know what happens when z is much, much greater than L. So just looking at this, if you picture, you can picture z getting big or L getting small, whatever you want. This term has an L upstairs. Actually, we are, yeah, so looking at this term, this is, I guess, the one that we're more concerned with. When z gets much bigger than L, downstairs, this will be basically the square root of z squared. So then we get a z over z, which will cancel with this minus 1, and the x hat component will just go away. Right, which is what we would expect as we get further and further away from this finite line charge. It will appear to shrink down smaller and smaller until it's just a point, and we only care about the z component. All right, so this x hat term will go away. So on this side, on this end of things, let's write this out a little bit. All right, so we're going to end up with just an L over z. So we have a 1 over 4 pi epsilon naught. We've got our lambda L from this piece right here. And then down here, the z is going to dominate this denominator right here. Where am I? So, yeah. So we have a z right here. And then, let me just write right on this. This term right here is also going to go like square root of z squared. And we just get a z, a factor of z. So we have one factor of z downstairs here, one factor of z downstairs here, and we get our z squared. All right, so, oh, and of course this is in the z hat direction. All right. So long story short, as we increase z to where we're far, far away from this line compared to the length of the line, this is the situation that we get. The field can still be very significant because, we can make lambda as big as we want. But just looking at this, we have our 1 over z squared dependence, 1 over the distance squared, just what we would expect. And then this term right here, lambda multiplied by L, linear charge density multiplied by a distance or a length, that is just a Q. So there we go. So we've recovered our electric field for a point charge right there at the origin.